Hi, welcome back. In this lecture, I'm going to describe the first way to use arrays. I'm going to use the list. I'm going to talk about the different features of list and consideration about memory usage in lists. By the end of this lecture, we'll be able to describe the properties and the features of a list. You will be able to describe how the list appending operation works and also describe an operation that is associated to appending, that is the over allocation mechanism. Finally, you will be able to evaluate what is the impact and the consequence of resizing and over allocation. As I mentioned in the previous lecture, lists are dynamic arrays that have basically two features that are shown on these slides. First, they are dynamic arrays that allow us to modify and resize the data. So the first characteristic here, you have on the top, we have a list with this array here, and then we modify one of the elements. So this is 0, 1, and 2. So we're modifying this element and then put 2 multiplied by the element of the list with the index 0, so is 5, so this is going to become 10. So this is very different from the tuples. They are not going to allow to modify the value. So the first characteristics of list is that we are allowed to change a value. The second important feature of a list is that we can resize the array, so we can add additional elements to the list and make it grow. So for instance, we have our list, original list here. We modified one element. We check what is the size of our list. We got 6, 1, 2, 3, 4, 5, 6. That's correct. And then what we do, we are adding one element here at the end of our list. We print it, and we got the list with the additional number at the end of our list. In this case, the length of the array is 7. So just to summarize this slide, lists are dynamic arrays that allows to modify the values and also to append additional elements at the end of the list. So let's talk about the operation of appending and resizing a list. So when a list of size n is first appended to, Python creates a new list. So it creates a new list that is big enough to hold the original n items. So there will be a copy operation from the old n items to the new list, and then we add the extra element that we want to append. However, Python, instead of allocating the new list with the size n plus 1, where n is the size of the list, and then 1 is the additional element that we are going to add to the list, Python does like a trick. So instead of allocating n plus 1, it actually does m items are allocated, so more than n elements are allocated. So instead of having m plus 1, right, we having n plus x, where x is typically is larger than 2, or some big number. We'll see how this number x is actually chosen. So the important point is that a number of extra items are allocated. So not just one more, but many more. Right? What is the motivation for this? Well, the motivation is that if we do one append, that's probably the beginning of many appends. So we're going to have. So what we want to do, we want to minimize the number of allocation and copies. And remember that each append is we are allocating a new list and then we are appending. What we're going to do, we are going to allocate not just a new list of size n plus 1, but n plus x, where x is a number of extra elements to avoid to keeping allocating as soon as we have a new element. So by requesting extra space, we can reduce the number of times of this expensive operation, that is the allocation. And also the total number of memory copies will be reduced. So both the memory allocation, as we said before, and the memory copies are very expensive operation when it comes to memory. Let's look at the operation on how to calculate how much extra space, how many extra elements we want to allocate. What the values that we call x in the previous slides. Well, in this case, we have m that is in this case is the size of the new list. So if you look at on GitHub on how this is actually implemented in Python, whenever we appending, we allocated a new list with the size here new allocated that is the new size plus a shift operation. The way to calculate, we take the n, that is the size of all the list, and then we do a shift operation plus addition. So in case here, when we have, for instance, for array between one element and 4, we actually always allocated the 4 elements, right? So even in the case we are allocating one list with one element, we actually over allocate for 4 elements. In the case, for instance, in the range between 36 and 46, we over allocated up to 46 elements. Again, if we have a list only containing 36 elements, then we are over allocating to have the possibility of storing up to 46 elements. So as soon as we reach the 46th element here, what we are doing this new allocation and increase the size. So we have this nifty formula here that is coming from the Python formula for allocation. So the important point here is that whenever we do resizing, we do a new allocation. We are not doing an allocation for just one element, but we are over allocating for more elements to be added. So as we append data, we utilize the extra space and increase the effective size of our list n. N grows as we append new data until n is equal to m, that is the over allocated list. Then we do this new allocation. So let's see at the impact of allocation. So this plot here has the size of the list, and then on the y-axis we have the number of elements that have been over allocated. So there is this extra room that we are allocating. So just to give you an example, in this plot here, if we have a list with 8,000 elements, we are going to have a number of elements that have been over allocated. In case that allow us to avoid an extra allocation whenever we adding new elements. So in this case, for 8,000, we're going to have 600 more elements that have been allocated. That's quite a lot, almost 10%, or well 8% or so. So Python will always allocate it, for more memory. In this case, if we have a list with 8,000 elements using appends, what Python is going to use is 8,600 elements. It's over allocating with the additional elements. In this case, 600 elements. As I mentioned, the pending operation is the following. We have the old list. We create a new list. We allocate a new list with the size that depends on this over allocating mechanism. Then we copy the old list in the new one, and then we add the extra element. So in this case here, for instance, we have a list with 1 and 2. We do an appending operation of 3. As you probably remember from the previous slides, whenever we have 1 to 4 elements in the list, we are allocated for 4. So what we're going to do here, we are going just to append our element and then copy from the previous list, right, and then append 3. If you append then another elements, in this case is 4, there is a space. When we append the 5, what we need to do is to do a reallocation. So in this case, we're getting more over allocating space. We copy the operation and then we add our operation. So the important part of these slides is that whenever we do an appending operation, there may be an over allocation and there might be a copy of the old list into the new list. And that, of course, takes quite some time. So let's look at the computational cost, both in memory and in execution time. The first experiment that we're going to do, still using IPython. In this case, I'm going to load this memory profiler in IPython using the magic loadExt memory profiler. And then I'm going to check what is the memory consumption for creating a list. So here we are creating a list using this so-called list compression technique. So that's one way, and the other way that I'm going to use is to create a list by just appending this value. So I just multiply by 2 I and keeping adding. So these two things, these two codes, they do exactly the same thing. However, the way to create a list is different. The first one is called the list compression, the second one just appending. Right. So from this one, we will expect to over-allocating and this copy operation. So when we look at the memory usage given from %memit command, and then we check the memory performance, we get two numbers. One is the peak memory and the other one is the increment. So the peak memory is a value, basically the maximum memory that we are using in our code. So it's not very much useful, right? It's just one value. The most important value here is actually the increment. That is the difference of memory usage between the peak and when we start using our code. So in the case of list compression, we saw that this creation of this list took 3.52 megabyte just to create, to fill this list. In the case of actually appending, we saw that it takes 10.3 megabyte. So roughly 3 times more space when we create it just by appending versus list compression. So that part corresponded to the memory usage, and the second part here it corresponded to the execution. In this case, I'm using magic time it command that basically tell us the time. In the case of list compression, we get 3.35 millisecond. It's quite big, but if we created the list by appending values, is even larger. So 4.88 millisecond. So why is that? Well, we know that when we do this appending, we have extra allocation, right? So we're keeping increasing the list over allocating, and also we have this copy operation. So this is the last slide of my lecture. To summarize, lists are dynamic arrays that allow us to modify the values and resize the data. So these are the two important features of list. The appending operation creates a new list that is big enough to hold the original n items in addition to extra ones that is being appended. We saw also that when we adding elements, the Python virtual machine over allocates to avoid many allocation operation. Right? The reasoning is that if you do one appending, it's probably the first one of many other ones, so we over allocated. And the last point I want to make is that appending and over-allocation strategies come with the overhead, both in memory and in time. This is the last slide of this lecture, and talk to you soon.